This is Warren Rixon, and this is my final presentation for MEMS 5001 titled Optimization of Operating Efficiency for Electric Induction Motors. Single-phase induction motors are an older motor technology. They are reliable and low cost, but they have low operating efficiencies. New motor technologies are becoming cheaper every day that have higher efficiencies and have begun to replace single-phase induction motors in many applications. My objective is therefore to create a genetic algorithm to optimize the operating efficiency of an electric induction motor with the hopes of making it a more competitive option in the market today. An overview of the method I'll be using a genetic algorithm function in MATLAB. I will pass 3 design variables to an executable function that uses a proprietary motor simulation software from the company I work at called NEDEC Motor Corporation that calculates performance and constraint values. If a constraint is violated, penalty points will be added to the ejected function value. This will then return a design vector that will correspond to a motor design with the optimal full load operating efficiency. The 3 design variables I've chosen to use are stack height, magnet wire turn count, and magnet wire size. All 3 of these design variables need to be kept to discrete values. For this algorithm, I've programmed 8 discrete options for stack height, 22 for turn count, and 27 for wire size. This corresponds to the total design options of 4,752. These design variables are put into a vector and passed to the objective function in MATLAB. The objective function is simple. It's the calculated expected efficiency for the motor design. By using the negative of this value, the GA function in MATLAB is able to attempt to minimize this and therefore find the maximum efficiency. The 5 constraints I'll be using, 2 of them are design parameters, full load torque and full load speed. The other 3 are space limitations due to the amount of space inside the stator teeth of the motor. If a constraint is violated, 50 points are added as a penalty to the fitness function, making it a less desirable option to be apparent for the next generation. I've decided to compare this to a control value. I selected a 6th horsepower, 850 RPM design that has been in production for some years now. In the context of this algorithm, the design vector for this design is 51814 and has a calculated efficiency of 37.32%. So that will be the efficiency we're trying to beat with this algorithm. First time I ran this algorithm, I kept all the options as they come in MATLAB as a default. I was able to achieve an efficiency of 48.5% with a design vector of 8, 5, and 9. This is 11 percentage points better than our control. I was able to do so with 69 generations, which is not very many generations. However, I wanted to see if we could cut down the amount of times the function is called. First thing I did is I tried to limit the population size to 20. Still able to achieve the same design vector with the same efficiency with only 20 or so more generations called, which cuts down on the amount of times the function was called. The other thing I attempted to do was limit the generations to 20. We were able to achieve the same design vector with the same efficiency. However, I would say this was not as good of a run as the mean penalty value was much higher than the best penalty value at the final generation. This is a chart that summarizes the findings. You see I have a total 4,752 design options. We were able to find the best one with a population limit of 20 at only 1,760 function calls. So to look at this, we were able to improve the efficiency by 11%. However, I do want to note that it always chose the largest stack size, which is known to increase the efficiency. The chances are that the control motor design was made with cost in mind. So I ran this algorithm one more time by limiting the stack height to what we found with the control design, and I was still able to achieve, after 67 generations, an efficiency improvement of 5%. So after all this, I would say that the genetic algorithm is successful in finding an optimal efficiency for electric motor design. In the future, this could be incorporated into the motor simulation software to take some of the guesswork out of the job of the engineer. Thank you.